Okay, thanks, Sarah. Many thanks to the IOE for giving us a chance to talk about the work in our group, and especially Kayode to talk about his part of his PhD dissertation work studying the composition and evolution of smoke produced by prescribed fire. Sarah said, I'm Rob Walker, department head here in chemistry and biochemistry. I'm also the EPSCoR Track 1 project director. And been here, I guess, since 2009. I was at the University of Maryland before that. And a common theme in our group is using various optical methods to study environment challenges, right? Interesting questions in either environmental chemistry, energy-related science, energy science, or biological systems. And that may seem pretty broad, but the underlying theme or the common denominator linking all of these is we look for, as a group, we are interested in societally relevant questions that can be addressed by using optical spectroscopy. And so to illustrate that a little further, this is something of an overview of what goes on in our group. We use a variety of techniques, nonlinear optical spectroscopy and fast fluorescence, to study chemical structure, organization, and reactivity at biological and environmental liquid interfaces. We use vibrational Raman spectroscopy to study energy conversion processes in solid oxide fuel cells. So these are devices that convert chemical fuel into electrical energy at temperatures of 800 degrees Celsius. And then a third area of our group is focused on combustion science, both air-independent combustion, so when the fuel carries its own oxidizer in it, and then what Kayode will talk about today is detecting the composition of smoke produced by fire that's consuming biomass. Kayode is a fifth-year PhD student in the Material Science and Engineering PhD program here at Montana State University. He has projects working on multiple fronts. You'll hear about one project that is nearing completion. We'll talk about that today, which is leading to a paper that will hopefully be submitted by the end of the semester. He wrote a very, very nice review about wildfire smoke and its evolution last year, published in the journal Fire. Appropriately, and he is intended to graduate come December of this year. I'm a faculty member. I could talk for hours on end without stop, faster and faster, but you're not here for me, you're here for Kayode. So I'm going to turn it over to him to have him tell you about the work that he's doing.
Thank you so much, Rob, for the introduction, and thank you everyone for coming here for this seminar talk today. I'm Kayode Fesomade, as they both said, and I'm the fifth-year PhD program, PhD candidate in Material Science program. Today, I'm going to be telling you a story. This story is what involves you and I as a resident of Bozeman. When you go out in summer, or when you want to go out in summer, you check the atmosphere, the outside. Is it smoky? Can I go out? So I'm going to be telling you about a statewide project which we call Smart Fire. We are getting into that. Most importantly, I will be telling you about prescribed fire, its impact on people and community. We'll be taking a deeper look at emissions factor. So let's start. Do you know that since 2001, Montana experiences about 430,000 of land being burned due to wildfire? That's sad. And this has resulted in a loss of about $146 million in Montana. So we can segregate Montana into 3 different regions based on the forest or the trees that has been grown in Montana as a whole. This first part in the northwest is an area where it's much colder and it's wet. And this area experiences wildfire in about 30, the frequency is about 30 to 100 years. Another one is eastern Montana. Here we have our majorly grasslands, And the occurrence of wildfire in this area is about 3 to 20 years. In southwest Montana, where we are located, where Bozeman is located, we have occurrence of fire in about 5 to 25 years. What does this mean? If you live your life out here in about 26 years, 27 years, there's high likelihood that you are going to experience fire at least 2 times. Okay, so with this fact in mind, on average, only 40,000 acres of land is being used to treat prescribed as treatment for wildfire through prescribed fire method, meaning 1:11 of wildfire to prescribed fire. It's what we are dealing with here. Okay. So what is this prescribed fire? I will tell you, prescribed fire is the intentional plan and use of fire to reach land management objectives. Then you ask me, okay, what are the land management objectives? I have them for you. They include limiting wildfire risk, especially in Montana, through fuel reduction. It includes ecosystem restoration. Some of us know about this ecology, and pest and disease control. Also, we use it in invasive species management and habitat improvement. So we talk about prescribed fire. One thing that comes with prescribed fire is smoke. And this is what some of us come in contact with. Smoke majorly can comprise of 2 things. Number one is gas, and the other one is suspended particles that we call particulate matter, or as some people call it, aerosols. So chemical gas composition can actually be as simple as hydrogen molecule, or can be as complex as aromatic hydrocarbons. So this picture you are looking here, it's a picture of prescribed fire exercise in Lobrecht, just outside of Missoula. And what you can see in the smoke is like CO, CO2, CH4, higher molecular weight compounds. And one other thing that comes out of fire smoke, smoke from fire, it's the particulate matter. So this particulate matter is a result of incomplete combustion, and we actually categorize or characterize them by the size of this matter. We have, so right here you can see PM10. This is the diameter of this particular size. That is about 10 micron. Just to calibrate you, if you pull a strand of your hair, that's about 20 micron. Meaning the size of the suspended particle is half of the diameter of your hair. Also, we have PM2.5. However, there is this particular size. We call them ultra fine particles. They are very tiny. They are PM0.1, and they are dangerous because of their sizes. They can easily penetrate into your lung, and they cause respiratory problems. Okay, so we know about the smoke. We know about the consequence. What are the how does this affect people? And I want to give credit to Libby and Katrina, their colleagues in this project. And so they actually this slide belongs to them. So what you are looking here is a poll, a survey that they took in Northwest United States, which actually include Montana. And what you are looking here is the distribution of people, like if a county is metro, or if it's like a rural area or something like that. And also credit to Kristen also for this. And what you are seeing here is the social distribution of people that are vulnerable to fire or smoke when we have a prescribed fire exercise. The red dots represent that particular distribution. So we talked about the consequence, we talked about wildfire, we talked about prescribed fire. And why is it used as a tool? Why do we use it? And we use it because majorly this prescribed fire, it's actually a very low cost and effective tool to combat wildfire in Montana. Also, it has been noted that areas of low elevation that has been treated with prescribed fire are highly resistant to wildfire. And we actually need this to restore our land management, to restore our ecosystem and the likes. So prescribed fire is good. What do we know about prescribed fire? It turns out we actually know a lot. We know so much. And I'm just bringing some of the research that has been done on prescribed fire for you. But majority of the prescribed fire research are being done in the southeastern part of the United States. What does this mean? What this implies is that the knowledge, the findings, the research that has been done may or may not be applicable to Montana topography due to several things: the topography of our land, the weather conditions, the thermal gradient, and the fuel type. So what I mean by thermal gradient is that you see when the sun goes down, how does the temperature drops? It differs from the way the temperature drops in Arizona or in Texas when the sun goes down. So we cannot transfer everything that has been done in the southeastern Pacific, Texas, Florida to Montana because of the difference in the fuel type. As a result of this, the Montana state government, in conjunction with NSF EBSCO, came about this big statewide project that we call Smart Fire. Smart Fire is an acronym for Sensors, Machine Learning, Artificial Intelligence, and Real-Time for Fire Science. And majorly, the purpose of this is to develop the knowledge and tools needed to assess the impact of prescribed fire on Montana landscape and community. I can tell you factually that this project comprises of 9 institutions and about 140 participants. And you can see the institutions, Montana institutions in this map here, in which MSU is one of them. In fact, MSU is the lead institution for this particular project. Then you tell me, okay, we had you. What do you do? In our lab, we fall under this fire science aspect. And what fire science means is that we actually try to reduce air pollution at regional scales. And we do this by studying the fire and smoke behavior as a function of field variability. There are other parts of the Smart Fire project. One of them is smart optical sensors. So majorly what these people do is they develop sensors technologies just to measure the field variability and then like thermal imaging and things like that. Also, we have the artificial intelligence and machine learning aspect. These people, they try to like build models to like see the trend in prescribed fire smoke and how it affects the community. And our very well beloved psychology, economics, and ethics people, they do one-on-one interview, they do interview and see how this affects people in Montana. Now, back to us, fire and smoke science. What am I doing? So in this lab, in our lab, we try to contribute to this project in 2 ways, 2 major projects. And the first one is the development of new tools to characterize emission. And we are using cavity enhanced Raman spectroscopy for this particular project. And what you are seeing here is a picture of our setup in the lab. It's just across the room for the 2 over there. Majorly, we send a laser of 633 nanometer through a bunch of optics. I won't bother you with the details. And majorly, the optics has like a cavity which is of high finesse, like 99%, 99.9% reflectance. So in the cavity, we have like multiple passes, like more than 100 passes of laser light. And this increases the scattering cross-section of our sample in it, thereby increasing sensitivity or detection limit of the instrument. And what you are seeing here is the product or the image from this setup. This is TM00 transverse electromagnetic mode. It's when the optics, everything is perfectly aligned, and we are getting a perfect Gaussian mode out of the instrument. And this is when it's going out of alignment, and we are getting like a split mode from the instrument. The purpose of the 2 projects that we are doing is to one, detect temperature of emissions, and two, to know what is being produced in emission or in combustion. But for the purpose of this talk today, I will be focusing on the second part of the project. So this project started about 16, 18 months ago, and it's a temperature-dependent emissions factor. Majorly, the method that we use for these two projects is vibrational spectroscopy. Before I go on, major pollutants that are released in prescribed fire smoke are methane, CO2, and CH4. And their vibrational frequency that we usually study are 2917 for methane, CH4, 1285 and 2349. And the difference between that is one is Raman active and one is IR active. That means you can detect one with Raman, you can detect one with the other one with IR. YCO comes about 2143 wave number. The numbers here are reported instrument limitation or sensitivity limit of instrument that has been reported over the years. So let's get down to it. Temperature dependent emissions factors. Everybody here know what temperature is. But what is emissions factor? So emissions factors is the amount or this of specific pollutant that is being emitted per unit mass of fuel that is burned. Mathematically, we can represent it with the ratio of the pollutants to the total mass of fuel that we are burning. The inference or the indication of this is when we have low emissions factor, that means we are producing a cleaner combustion or we are producing a more better, technically more cleaner combustion and vice versa. And majorly the ways that this emissions factor is being measured is we can measure it in the field when we have planned prescribed fire exercise or in the lab, as the case you will be seeing today. In the field, majorly what they do is they equip aircraft with sophisticated instruments like GC, gas chromatography, mass spectroscopy, and then the instrument, the aircraft flies over the area of prescribed burn, and then it can pick up smoke and analyze what is in the smoke, and then they can report the emissions factor. The problem with this method is what we are in contact with is about, say, 7-8 feet above the ground level. What they are measuring is about several feet above what we are coming in contact with, because there's chemical reactions, breaks one breaks, new molecules are formed as we go up. This is like one major accomplishment of this project is this fan. It belongs to the University of Montana in Missoula, and what it does is like we can now measure smoke composition from prescribed fire at the level that we come in contact with. So they take this van and pack it. There is proximity. They pack it close to where there is prescribed burn, and then they can do their analysis, removing the discrepancy between what we bring in and things like that. However, in the lab, for lab measurement, we can use instruments like GCFTIR, but for today, for what I will be showing you, majorly we are using TGA, which is a thermogravimetric analysis, and FTIR, that is a Fourier transform infrared spectroscopy. These emissions factors varies based on the fuel type that we have. Say, for example, there is a prescribed burning in Bozeman and there is another one in Missoula. And these two areas have two different types of forests being burned. The emissions that is being emitted from the two areas differs because of the type of the differences in the fuel type. And also the combustion phase, when we are in flaming phase and when we are in the smoldering phase, it affects the combustion. Most especially the moisture content in the biomass makes emissions factors different. So the knowledge gap and what we are trying to study, what we are trying to fill in for, it's that most of the emissions factor, like I said, are from southeastern part of the United States, and they have limited applicability in the Montana field and climate. And most especially the lab-based emissions factors that are reported as integrated value, like over the entire exercise of prescribed burning. However, what does each temperature, or what does the specific of emissions factors looks like at each time, at each temperature of the burn? And that's what we are trying to answer. And to actually do this, we put some things in mind. At the temperature range, we noticed that, okay, prescribed burn goes up to like 600 temperature. So we set our experiment to go into that range of 600 temperature so we can capture everything every information that we need to capture. And the temperature gradient, how quickly we can heat things up, or how quickly the fire burns up in the heat. And most importantly, we are putting at the back of our mind that the wildfire differs from prescribed fire. So the emissions factor we are expecting should be a little bit different. And also, the key species that we are going to be focusing on is CO2, CO, and then CH4. So to do this, we use this particular instrument, the TGA instrument. So what this instrument gives is, it gives a mass loss as a function of temperature. And for most of the biomass for most of the data you'll be seeing, it's Kentucky bluegrass unless otherwise stated. And this instrument actually range from ambient temperature to 1200, which is more than enough than what we need. 600 degrees is what we need. And then we can linearly heat things up to like 500 degrees C per minute. And it can sample weight up to like 100 milligrams. And that's the instrument specification. So TGA, this is a typical curve that you get from a TGA instrument. What you are looking at on the y-axis is the percentage mass weight loss. And what you are looking here is the temperature as a function of the temperature. What we actually did is we took the same biomass, but the blue trace is as harvested, dry, wet, and the red trace is dried biomass when the biomass contains less moisture. And one thing you can notice here is this particular bus A. You can see a massive drop up to like 80% of the weight of this as harvested coming off at before just around 100 degrees C. Another thing, if you look at, although for the as harvested, we can see another just small drop, just small mass loss in the biomass. And so for every loss here, it corresponds to emissions. That's when we get emissions from. So if you look at the dried sample, you can see like two major loss after this drop on box A. The box P is the first drop, and then the box C is the second drop. The takeaway from this plot is that as harvested, the blue trace comprise mostly of moisture, which is 80% of the weight of the entirety of the sample. But if we remove that moisture part, that is this trace B, red trace, we can zoom in on what is actually happening in combustion or in emissions process. And that is what we are seeing in box B and box C. And we actually, you see, they range from temperature of 210 to like 350 and 400 to 450 as well. But I can tell you it's 260 and 420, and I will show you why it's that temperature later on. So actually, what are we burning? Biomass can be dead materials or anything. And we know that our biomass is actually plant-based material. So this plant-based material, they typically composed of cellulose, hemicellulose, and lignin. These are the chemical structures of cellulose and cellulose, hemicellulose, and lignin. So majorly, the proportions of cellulose, hemicellulose, and lignin in each forest type or in each biomass differs from one to the other. What we did is we actually acquired commercially available cellulose, hemicellulose, and lignin, and we try to see what that looks like in practical. Um, so we tried to change or vary the heating rate from 5 degrees C per minute, 10 degrees C per minute, 50 degrees C per minute. It turns out the heating rate or the ramp rate does not really affect the emissions that much. So we just stick with the 10 degrees C per minute. However, one thing that stood out from this, okay, so these are the traces for the standard commercially available material. What stood out is that at 415, lignin was emitted. 323 cellulose came out, and then at about 260, hemicellulose came out. So if we transfer this, our standard, back into our sample, we can easily say at 260, we are losing cellulose and hemicellulose in the structure of the plant material. It's being collapsed. And then at 420, lignin is coming out. And this is actually moisture or water content. We can see it from the variation between dried and undried sample. And actually water comes off, evaporate at 100 degrees C. So it does make sense that everything is happening below 100 degrees C here. Again, don't forget, two important things. One is we want to know at what temperature these emissions are coming out. And the second one, we want to know what are we producing, what is coming out of, what is the smoke composed of. So I think to some certain extent, we can answer the first question that, okay, we know the temperature at which this composition or these emissions are coming out, but we can be more specific about the temperature. And to do that, we use derivative thermogravimetric analysis. Majorly, we just find the derivative of the TGA curve earlier on. And this is what the derivatives look like. The derivative curve looks like. And this is for the 6 hours dry, and this is for the surface state. In this derivative, if there is any slight drop, it's very sensitive that you can see like 10 drop sensitive. So you can see the small drop for the water content and the huge water loss in the surface state. And this is the first temperature at 260, and then the second one at 420 for the dried sample. And we can actually overlap that with the TGA curve, and it matched perfectly well. So we can be specific about the temperature in which significant emissions are occurring when we have a planned or prescribed fire exercise. 260. First temperature, 420, second temperature. Those are very important like temperature for this biomass sample. And to be more quantitative, we actually run several bunch of experiments. And what we find out is that this value is actually valid for 260 plus or minus 3 for our biomass. And on the lignin end, we have 438 plus or minus 7. For comparison, the standard is valid for 269 plus or minus 4, and then 416 plus or minus 10. Okay. Before we conclude on the first goal to know the temperature at which at which these things are coming up. I will not be talking too much on the Californian brom, but what I want to show here is that each biomass contributes to emissions in different ways, even though everything is coming out in, as emissions. So we took Californian brome biomass, and then we separate it with leaf stalk and seed. And it turns out they actually behave differently, and they emit differently, like in smoke. And also we did for a very common type of tree in Montana, like pine tree. This is what pine tree looks like. Majorly, it's not as complex as Californian brome. We lost some water, and then we have a huge loss. But for the purpose of this talk and for our time, I will not be focusing too much on this today. So again, first question answered. What temperature are these emissions coming off? Then, how do we know what is being produced? Maybe smoke is not so harmful after all. Maybe we are just paranoid. We'll see from here. So to do this, actually, we include one extra instrument This is Fourier transform infrared. And what we did is we took the exhaust or what is being coming off as gas from this instrument, and then we coupled it with this instrument. So we send the exhaust into the gas sample cell and FTIR. And we started taking a sample measurement at 250 degrees C, because from TJ we know that 260 is the significant temperature we are looking for. So majorly this one tells us the temperature, and then this one specifies what is coming out actually. It turns out that of the two major drop or the emissions that we have, again, don't forget that this part is just water. So that's not very harmful. We don't really care about that. But we see activities starting from like 200, 250-ish up to like 500. We see something coming out. And then what are they? Actually, I have like an expo, like a solution to the question. These are the material. Then you ask me, how do you know? Then, then I'll tell you. I know through this call. So this is what you see from FTIR plot. And what you are seeing on the y-axis is the absorbance. And what you see on the x-axis is a function of the wave number. That is the vibrational frequency. That's what I showed like in tables earlier on. So we did at 250, we did at 300, 350, 400, 450, and 500 degrees C. And what we notice and what we see is that at lower temperatures, we see emissions of CO. So you can see it labeled here. CO is the one coming up at 2175 for the peak assignment. And then methane is the one coming up at almost 3000. That's like 2900. And then this big one is CO2. So what we notice is that at early hours of prescribed fire burn, or when we start the burn, we start emitting CH4, methane, and CO. However, when we increase flaming and when the flaming is sustained, we start with the production of CO2, and CO2 actually becomes more increased as we go on. Okay, so we are producing three things. We can quantify this, put it in a number form using this emissions factor. Majorly, again, so that you don't forget, this is what emission factors looks like, and that this formula. It turns out this very popular man in the science world, Pierre Lambert, he gave us a lot before he left us, and it's very, very useful in today's world. And the formula is absorption equals molar absorptivity times concentration times the length of the cell that we are dealing with. So with what it left us with, we can easily calculate our emissions factor. So to do the emissions factor, we did something like a simple experiment for instrument calibration curve. And it turns out our instrument is about 0.25, and the constant for our instrument is about 0.25%. It's very, very close to what is out there for most instruments out there today, 0.24 to 0.26. Okay. From there, we can calculate our concentration fraction. This A here again is the absorption from our FTIR plot. Okay. And then from there, we know our molar volume is 24.45 liters per mole. And we can actually calculate our concentration of CO2. Say we are doing the emissions factor for CO2 in this particular example. It turns out that the concentration of our CO2 is 0.1152 grams per liter. And we can estimate the mass in grams of our CO2 that is being emitted from our experiment, because we are sending gas at 25 milliliters per minute, and we are taking the experiment at 2 minutes. So the total mass of the mass of CO2 that we are emitting is this value, 0.0578 grams. Again, we are trying to get emissions factor. So we know this mass. However, we know the total mass of sample that we are sending into our instrument from the start of the experiment, which is this. If we know these two values, then we can get our emissions factor. And our emissions factors turns out to be 442 kilograms, grams per kilogram. What is being reported here in papers like 1500, and the discrepancy here is because we are only taking for like a small fraction of our time. We are not taking for the entirety of everything. If we integrated everything over, then we get about 1500 grams per kilogram. So, we can quantify our emissions factors based on different temperature, and then we can put it in a pictorial or figure form. And I want you to focus on, so the blue trace is CO2 that is being emitted in our biomass, and the blue trace is the CO2 is green trace, and then the red trace is for CH4. And if you can see, as we go to 300 degrees C, the production of CO2 drops. However, when we increase the intensity, that means we are switching from smoldering flame to smoldering, from smoldering to flaming flame. That is, the intensity of the burn is increased. You can see we started producing more CO2. And as we reach like a climax at about 450, and then as we are going back into smoldering nature of the flame, CO2 production drops. For methane, we actually produce methane at earlier stage of the combustion of the oxidation process. It was sustained. It increased slightly, but the margin was it's not too much. It's like we sustain the level of production of CO2 all through the experiment. What this means in essence is that when you have a prescribed burn, the early stage of the fire or the later stage when the fire is being put out is as dangerous as what is coming out when the fire is intense, which the emissions factor they are reporting in does not capture the difference in these stages. So I will conclude today. I will conclude my presentation with these three major points. The first one is that combustion phase influences emission composition. That is, emission from flaming combustion differs significantly from emission from smoldering. The second one is we form CH4, that is methane, at a very low temperature, although it's sustained over the entirety. And lastly, the smoke composition is temperature dependent. It's a function of temperature and time. So when the firefighters go to control maybe the fire, like wildfire or prescribed fire, at the early stage, they're actually producing more CO. And even at the later stage, when the fire is going down, they're actually producing more CO. And I can tell you, CO is more dangerous than CO2. You can ask the chemistry colleagues. With this, I want to conclude my presentation today. I really want to thank my committee member. I would like to thank my advisor. Again, Dr. Rob Walker. He is the best. If I have to choose over again, start PhD again, I will choose Dr. Rob Walker. And also, I want to really thank all the Walker Research Group, Dr. Josh Shinru, that taught me all I know about optics today. Dr. Doreen Brown, Kim, Sam, and the entirety of the Walker Research Group. And I want to thank you for listening to me talk about my research for the last 30, 40 minutes today. With this, I say thank you very much, and I will take any questions that you have.